These are notes on the pH scale and neutralization. It's 19.2 and 19.4 in your book. You don't have to worry about 19.3. That gets into a concept we're not going to deal with. If you're interested in it, by all means, read ahead. And I also have here, back by popular demand. Annika may come in later, but she's not sure. So this is a picture of the pH scale. I picked it because it has a lot of different substances on it, so you can kind of see what different things are. So anything below 7 is acidic, is known as an acid. So
orange juice is the pH of 4. Bananas is the pH of 5.
So you'll notice bananas are weakly acidic. Remember, we were talking about bananas earlier, and I said I didn't know about that one. What about that one?
Battery acid, pH 2. 2 pH.
Hydrochloric
acid is 0.
Yeah, so hydrochloric acid is a pH of 0. I'm actually going to add something in here. And that is hydrochloric acid that is 1.0 molar. Okay, so if you have hydrochloric acid that is less than 1.0 molar, that's a higher pH. If it's more than 1.0 molar, you actually have a pH that could be in the negative numbers, which is kind of interesting. So then, anything above 7 is basic. So, for example,
bleach has the pH of 13. Baking soda has the the pH of 9. Eggs has the pH of 8. And sodium hydroxide has the pH of 14.
Yeah, and once again, that's a 1.0 molar solution, so just kind of keep that in mind. I don't know why my mouse is so screwy today. And then, in the middle, we have 7, and that's called neutral. Neutral just meaning not acidic or basic. And so things that are neutral are?
Pure water.
Pure water.
Pure water, pH 7. Milk, pH 7. Human
saliva. Do you know what human saliva is?
No.
Spit.
Ew! Blood has the pH of 7.
Yeah. So all of those things are considered neutral. One thing that is interesting, and you're going to see why about the pH scale, is each number on the pH scale is 10 times more acidic or basic than the previous or following number. So for example, pH of 2 is more acidic than pH of 4. Now you might think it's maybe twice as acidic because 4 divided by 2 is 2, or 2 times 4, something like that. But in fact, between 3 and 4, 3 is 10 times more acidic than 4. And 2 is 10 times more acidic than 3. So one might think now that 2 is 20 times more acidic than 4, but that's not true. It's actually 10 times 10, which is?
100.
100 times more acidic, exactly. And so each number is 100 times more acidic than the previous, which starts to get to be a pretty big deal. You know, when you're talking, you could, get 1,000 times more, and it's just a difference of 3 numbers. All right, so let's break this pH scale down mathematically. Those of you who like math are going to like this. Those of you who don't, aren't. All right, first we're going to talk about this thing called the self-ionization of water. Do you know what that means?
No.
No, neither does anybody else here, except maybe me. So you guys know what ionizing means, right? It means it's going to form ions. Well, you know that, for example, if you dissolve salt into water, you get sodium ions and chlorine ions. Water actually ionizes itself. So we have this equation here. Okay, so we get this equation that Mia's going to explain in a minute, but first I want to show you that one of these H's from here is going to come over and join this. And so this whole reaction is?
Water plus water, you H3O plus
aqueous, good.
aqueous plus OH minus aqueous.
And if you remember, this H3O plus is called hydronium. This OH minus is called hydroxide. We all know OH minus is hydroxide, or if you don't by now, you should. The H3O plus being hydronium, in some books, including your own, you're going to just see it as H plus. Some books will say H3O plus. It essentially means the same thing. And it's that hydrogen ion or hydroxide ion, or I'm sorry, hydronium ion or hydrogen ion. It really does mean the same thing. I've always learned it as H3O plus. I feel like in college texts I've seen it's H3O plus, and so I'm going to go with H3O plus, even though your book does say H plus. So what this equation really is here, and this certainly is not balanced, and that's okay for right now. Obviously, well, here I can even balance it. This would be a 2 here. There, now we're balanced. But this equation is 2 waters yields a hydronium and a hydroxide ion. Okay? And water just does that to a certain extent. Now, if we go and look at the KEQ of this equation, and this is why we do acids and bases following equilibrium, because we're going to use some of those concepts. The KEQ is simply the concentration of hydroxide of hydronium times the concentration of hydroxide. We don't figure in the H2O liquid. Those people who learned more and did the extra credit test, you know that the concentrations of a pure liquid really don't change, because what we're then talking about is density, and the density of a liquid is the same regardless of how much you have. So the concentration of hydroxide and times the concentration of hydronium, or the KEQ, for water is, or for any aqueous solution actually, is 1.0 times 10 to the negative 14th. So if you think Le Chatelier, if we increase the amount of hydroxide, that's going to push the reaction this way, which will decrease the amount of hydronium, and vice versa. Okay? Always giving us a KEQ of 1.0 times 10 to the negative 14th. All right, so let's see how this applies to pH then.
pH continued. pH is the
Concentration
of
hydronium.
hydronium ion.
And hydronium ion is H.
H3O plus
Solution.
solution.
So pH is the concentration of hydronium ion in solution. It's what concentration you have. Keeping in mind that the concentration of hydronium times the concentration of hydroxide is going to equal 1.0 times 10 to the negative 14th. So here are 3 numbers. Okay.
1 times 10 to the negative 6, 1 times 10 to the negative 7, 1 times 10 to the negative 8.
And so just to practice, for those of you who struggle a little with your exponents, are these numbers going from smallest to greatest or greatest to smallest? So is 1 times 10 to the negative 6 the smallest or the greatest number? What's your thought? Take a guess. Okay, so Annika thinks they're smallest to biggest. What do you think?
Smallest to biggest?
Yeah, it sort of makes sense that they're smallest to biggest. In fact, though, hopefully you high school students know that these are actually biggest to smallest. It's not backwards, because remember, 1 times 10 to the negative 6 has fewer zeros before, it only has 5 zeros before the decimal, or after the decimal, whereas 10 to the negative 8th has 7 zeros before the decimal. So 10 to the negative 8th is actually smaller than 10 to the negative 6. And so that's important to understand when we start talking about why the lower numbers are more acidic. So the equation, oh, actually, I don't get to the equation yet. That must be next. So if the concentration of hydronium is greater than the concentration of hydroxide, or the hydronium ion concentration is greater than 1 times 10 to the negative 7th molar, that's an acidic solution. If hydronium ion is less than hydroxide, or hydronium ion is less than 1 times 10 to the 7th molar, that's a basic solution. And so from this, you should be able to figure out what a neutral solution is. It's when the hydronium and hydroxide concentrations are they're equal, or the hydronium concentration is, do you remember how to say this? Yeah, say it. That's negative.
1 times 10
to the negative 7.
to the negative 7.
And so that would be neutral. And if you, again, this is where you have to remember your exponents. Notice, like let's take this neutral solution. So it's 1.0 times 10 to the negative 7. If we then, so that would be our hydronium, but we know neutral is that equals hydroxide. So that would be 1.0 times 10 to the negative 7. And if you remember, when you are multiplying exponents like this, you add the exponent. So Annika, what's 7 plus 7? 14. So this is 1.0 times 10 to the negative 14th. And that's what we said, that the hydronium times the hydroxide is always going to be 1.0 times 10 to the negative 14th. At room temperature, by the way, because again, KEQs can change with temperature. All right. Yes. Say it.
Calculating pH. pH equals negative log H3O plus.
So the pH is the negative log of the concentration of hydronium.
POH equals negative log OH minus.
Yeah, so there's also this thing called the POH, which is the negative log of the concentration of OH minus. Now, pH plus POH equals 14. And so that's where, if you're looking, notice the KEQ is 10 to the negative 14th, pH plus POH is 14, the pH scale goes from 0 to 14. So all of this is starting to make sense, hopefully, or seem like a crazy coincidence for those of you who it's not making any sense to. So one of the things to understand is the inverse of a log is 10 to the x. So we can obviously use like this equation if we know the concentration of H3O plus. We can use this equation to figure out the pH. But knowing that the inverse of a log is 10 to the x can help us, if we have the pH, figure out what the concentration of H3O plus is. And we'll do some of that practice in class, but it's just algebra, except that now we're using logs and 10 to the x's. So, for example, 10 to the negative pH, because we've got this negative here, okay, is the concentration of H3O plus. So let's have an example.
What's the pH of a solution where H3O plus equals 3.54 times 10 negative 6?
So go ahead and pause the video, figure that out. You should have gotten pH is the negative log of 3.4 times 10 to the negative 6, which is 5.47, which makes it a weak acid. if you're totally confused at how I got that on your calculator, I think the easiest way of doing this, you can certainly do negative log 3.4 times 10 to the negative 6, or if you're a little confused, I think you can do log, so hit the log button and then 3.46 times 10 to the negative 6. Remember to use the EE button for the exponents. Go back to what we learned earlier. Some calculators get really confused if you're doing like times 10 raised to the power. And then remember, you're going to get a negative number. Well, pHs, for our intents and purposes in this class, are positive, so then you just drop the negative. Now, those of you who are interested in where the significant figures come from, this is touched on in your book. It is in chapter 19, somewhere in the pH, so it's got to be in 19.2. 3.4 has 2 sig figs. Now, 5.47 has 3, but when we're talking about pHs, it's only the numbers past the decimal point that are significant. So the 2 sig figs is why we bring this to 2 decimal places. I know, just what you didn't want right now. All right, let's look at another concept. This concept is called
Neutralization.
Neutralization, and it is how acids and bases cancel each other out.
The products of a reaction between acids and base are usually water and salt.
Not always water and salt, because as we saw when we looked at Bronsted-Lowry acids and bases, they don't have to have an H or an OH, and in order to get water, you need the H and the OH. There's always a salt. Now, what do we think of when I say salt? When I say salt, what do you think of? What do you think of? Come on.
Acid?
You think of an acid if I say
No.
Mia, pass the
No,
salt. You think I'm talking about acid? What does salt mean to you?
Dried up water.
Okay. It actually comes from dried up seawater. Yeah. Yeah, they take the water, the seawater, they evaporate all the water. It actually happened naturally, and so they find places where that happened. But right, something you eat, right?
Yeah.
Okay. In acids and bases, salt is a much more broad term. So a salt is an ionic compound with a cation from a base and an anion from an acid. So really it's any kind of ionic compound that comes from a reaction between a base and an acid. Now, salt, as in table salt, absolutely does. It's the product of HCl and NaOH, and you get NaCl, which is table salt. All right, so
what are products of neutralization reaction between
hydrochloric
acid and calcium hydroxide?
So go ahead, pause the video, figure it out. This is essentially a reaction problem. And you should have gotten 2HCl aqueous plus calcium hydroxide aqueous. Now, this is where you've got to go back to your knowledge that hydroxide is OH minus, calcium is 2 plus, so there's 2 of them, yields liquid water, and this now, we would say this is the salt, CaCl2. Okay, so on your properties of acids and bases worksheet, initially I had one that was a salt, and that's where that came from, because originally that table was label it acid, base, or salt, but I hadn't taught you salts yet. One of the things to notice here is the H plus ion, and notice there's 2 moles of it, and here's the hydroxide, and notice there's 2 moles of it. So in order for complete neutralization to take place, and obviously that would end up being pH of 7, you have to have equal concentrations of your H plus ion and your OH minus ion. So that's why that works out that way, and that's why you end up with a neutral solution.
Titration.
Okay, so this is a new concept having to do with neutralization. Can you read that?
Yeah. Use a measured amount of a known solution to calculate the concentration of an unknown solution.
Okay, so essentially what we're doing is, if we understand how neutralization works, that we need equal moles of acid and base, and we have like a certain amount of a known solution, and then we have an unknown solution. We could say, well, if I need this much of this known solution, that means it's this many moles, and so I know there's this. Okay, let me break this down differently. Let's say I have a known acid. Okay, I have a known concentration of an acid, and it takes a certain number of milliliters of that acid to neutralize this unknown base. Well, I can calculate how many moles of that acid I used. I know it's going to be the same number of moles of base, and so then I can calculate the molarity of the base. And I use what's called an equivalence point. And the equivalence point is when the moles of the acid equal the moles of the base. And that, of course, is when the solution is neutral. So here's a practice question. How many moles of sulfuric acid are needed to neutralize 0.50 moles of sodium hydroxide? This is essentially stoichiometry, and you can figure it out. Pause the video, see what you can do, and then start it again. Oh, did I not have an answer to that? Oh dear. All right, let me get an answer. Okay, here we go. I actually put it on a different slide. That's why I got confused. So, first you need your balanced equation. So sulfuric acid is H2SO4. You know that it's the sulfate ion because 8s go to ic, and then sulfate is SO4 2-, so it's H2, plus 2 NaOH. And that, notice, is how we're going to get our 2 moles of H plus and our 2 moles of OH minus. Yields Na2SO4, so sodium sulfate, that's the salt, plus 2 waters. And now, again, it is, so now, if you didn't get that far, pause it now and see if you can go now. If not, you can keep checking. So, we have 0.5 moles of NaOH. We know it's 1 mole of H2SO4 to 2 moles of NaOH, so the moles of NaOH cancel out, and that gives us 0.25 moles of H2SO4. So it takes 0.25 moles of H2SO4 to neutralize 0.5 moles of sodium hydroxide, and that's because we don't have a 1-to-1 ratio here. Okay? All right. It's thinking. So here's another titration example.
How many
milliliters
of 1.5
molar
NaOH is needed to
neutralize.
Sorry.
That's okay.
45
milliliters
of 2.0 HCl.
Cl, actually. Sorry. But that's okay. A lot of my students are going to think HCl too, and they should know better. So, see if you can figure this one out. This is now what I was talking about, like you've got kind of an unknown situation here. How much do you need? So the first thing you need is the equation. NaOH plus HCl yields NaCl plus H2O. There's your salt, your table salt. And so we have 0.045 liters of solution times 2 moles per 1 liter. So that's this information here, that's my known, right? I changed the milliliters to liters, so that cancels. So that's that, times 1 mole of NaOH to 1 mole of HCl. Some of you are going to say, oh, I don't need that because it's 1-to-1, but put it in because on the last problem you did need it. So this is my changing moles to moles. And then I know I've got a 1.5 molar solution, so it's moles of NaOH to liters of solution. And so that's going to give me my liters of NaOH solution. That ends up being 0.060 liters of NaOH solution, or 60 milliliters of NaOH. So please feel free to put questions on the comment section of YouTube or ask in class. Have a good night.